and I did not change anything. Let me run the simulation again and see whether my output voltage goes to 20 volt automatically. See, it went there. Okay, I did not change duty ratio, nothing I changed. Only reference signal I changed. It naturally goes to 20 volt automatically, right? That's the beauty of this PI controller. So, if you ask a question, can I bring it back to 12? So, just by changing the reference value, the desired value, right? See whether it comes back. Let me run it again. See, it came back. No problem. So what it means, this interesting, this controller, it can automatically adjust the duty ratio or the reference signal, okay, so that you can make this output voltage follow its desired value. In case you are wondering, if I make the input voltage change, let's say it become 54. So reference is 12, input voltage has become 54. And let me run at this condition. So see, there was the initial some disturbance, right? Let me zoom it. But then it again came back to 12. So that means it is taking corrective action. See here, this is the place. I increased the input voltage to 54. And there was some disturbance, of course, because I increased the input voltage. But it took corrective action and your output voltage become 12 volt. It came back. From this, let's change the input voltage to 40 volt. And same other thing remaining same, let me run it again. See, there was some initial disturbance, but then again it goes back to 12 volt. So how all these things are being done? These are taken care by the PI controller automatically. You tell it what to do, it is somehow doing it, right? So that's the beauty of PI controller, which is extensively used in several applications, be it motor controller, battery charger, everywhere. Okay. Right. So now let me take up some of your questions. In case you are referring to this, so in this entire phenomena, see, input to the comparator, one will be the reference, one will be the sawtooth. Okay. One is reference, one is sawtooth. The reference will be decided by the PI controller. Sawtooth is fixed, as I told multiple times. Okay, Mr. Anshu said, please share Google Drive link. Yeah, this could be maybe the 10th, 15th time I am sharing. Not a problem, I can share again. So this entire study material is kept in the Google Drive. I'll share the exact simulation file. So those who are looking for this simulation file, it is kept here in this folder. Okay. So here is the simulation file. I hope that also taken care of. Okay, so there is a question. I'll go up. Please repeat before sawtooth. So I'll repeat this part again. I think I repeated several times, so I won't repeat it anymore. I'll repeat it. What I'm saying, I'll repeat it after 10 p.m. because this PWM part we discussed in the last class. Today also we discussed 2 times. I'll discuss it again after 10 p.m. so that I can cover other important parts. Okay, there is a question. This frequency is signal right? Sorry, I did not get your question. I'll give you mic access at the end of this session so that you can ask me question. Okay, more examples like problems can able to understand. So thank you for your questions. If you want me to solve several problems, I can do it, but then you need to give me several sessions, right? No problem, I can do it. But since there is a shortage of time, I am giving you study material where a lot of problems are already solved. In fact, in my slides also I give you solved examples. First, attempt them, then I'll tell you from where to study more, okay? To be honest, I also feel like there has to be more problem solving sessions. But then, if you want to cover a one semester subject in 2-3 days, you cannot cover each and everything, right? Now you have to decide whether you want to understand the concept or you want to practice. So there has to be trade-off. That's what I'm trying to say. There is nothing wrong or right. So some workout problem examples are already given in my slides. That's what I told you. What you can do is, see, there are some power electronics reference book I gave. Most of their PDFs are available online easily. Okay. Simply go to the particular chapter. For example, which topic we are talking about? DC-DC converter. In all these power electronic books, there will be DC-DC dedicated chapters. Each of those chapters, each of these books, there will be worked out examples. Just go through them. And I am pretty sure if you solve those problems, or at least go through them, you will understand more or less. Still, if you're stuck, for example, let's say you open book number 1 and you go to DC-DC converter, you target problem number 1. Just solve the problem. You need not solve on your own. Look at the solution. If you're stuck, let me know tomorrow. I'll help you. But some effort has to come from your end also, right? Give it a try tomorrow. If you're stuck, tomorrow I'll solve it. No problem. Take any of this book as reference, solve one problem, try to solve. If you're not getting it, I'll help. No problem. Unfortunately, I cannot discuss each and every problem. It takes huge amount of time. Okay, there is another question. In short, about selection of LNC. Selection of LNC are very straightforward. These are just, you have to follow standard formulas. Let me know which part you want more in detail. I don't know, sounds like they're not showing up correctly. Okay, so for LNC selection, you see, this is just a simple equations, right? You have to fit in proper values, you will get their values, nothing else. What values you have to put in, that also one by one I explain. For example, for inductor, you have to fill in output voltage of V0. You know it is 12 volt. 1 minus D. D is duty ratio. For a 48 volt, 12 volt system, it will be 12 by 48. Standard value, right? Nothing. Frequency, again I'm saying frequency is the design choice. Higher the frequency, size of inductor, size of capacitor will come down. But your switching loss will increase. So it is a trade-off, right? Typically for DC-DC converter, 100 kilohertz, 50 kilohertz, these are good choices. For inverters like motor controllers, switching frequency 10 kilohertz, 15 kilohertz, somewhere there is a better choice. But again, let me tell you, selection of exact switching frequency comes after a lot of iterations. Switching loss you have to estimate, size of the inductor, size of the capacitor you have to estimate. You see whether it fits in your enclosure or not. So a lot of calculation goes at the back. One converter selection design itself takes several months. So I'm sorry, I cannot, I don't have that much time, and you also don't have that much time to go in that minute details, right? This is not a course to go into minute details. In few sessions, you have to learn power electronics, motor controller, autonomous driving, battery basics, battery charger, right? Vehicle dynamics, all those things, right? So it is practically impossible to understand each and everything in minute details. Please try to understand that. So third is inductor current ripple. As I told, we are going to select it 15%. So 15 by 100 into the inductor current. Okay. So buck converter, that inductor current rated value will be your output current. So how you get all these values? Again, I am saying just solve one problem. Please solve one problem. I'm pretty sure you will come up with doubts. That's what I'm saying. Tomorrow, I'll clear your doubts. But give it a try. Without trying, you don't know what is the problem. If I do everything on a spoon feeding basis, after 1 or 2 days, you will simply forget. Solve one problem. Deliberately, they see in the first problem, I did not solve it. I gave you all these equations and I am requesting you to solve. If you can't solve, there are solved out problems. But don't go to the solutions first. See, all the solutions I already given. But again, I'm saying don't go to the solution first. Give it a try. Then go to the solution. You will understand there is a reason behind it, why I said it like that. Still, if you can't get it, tomorrow I'll again come back to it and we'll solve together. No worries. Give it a try. You'll see it will be there in your good memory. There is another question, why it is sinusoidal? So, see, it is a L and C both are involved, right? It is a second order system. So, in case you have taken, I'm not sure, if you're from electrical engineering, you should, if you remember, there was a course called Fundamentals of Electrical Engineering or Signals and Networks. In those subjects, these topics are covered. If you are from mechanical, you will find it difficult. So, simple thing is that there are two kinds of energy storage system, inductor and capacitor. They keep on shifting their energy through oscillation mechanism. Okay, so that's why it is sinusoidal. Comes, goes back, comes, goes back. It's a two second order system, basic fundamentals. Had it been only inductor or only capacitor, you would not have seen this phenomenon. Okay, simulation step by step. I'm very sorry. Again, I offer my apology. It is not practically feasible to each and everything in detail. That's why I gave you the simulation model to study. Yes, so Mr. Saravana, I already submitted the simulation file to your folder. Mr. Shubhankar, you are very correct. I am also agreeing, but try to understand this MATLAB detail was actually not part of my so that you can understand something, right? You had a MATLAB training session separately. Why this signals going on horizontal lines in simulator graph rather than going populated on horizontal axis? Mr. Ansu, again, I'm very sorry I did not get your question. I'll give you my access after the class. See, when MATLAB plots something, there is a x-axis is always time, right? So it has to go horizontally, if I understand your question correctly. Any signal has to move on the x-axis because the x-axis is the time. So, but again, I'm saying I may not have understood your question correctly. Okay, yes, AI can be designed in those selection of these values. Tomorrow's session is 2 hours. In fact, I had requested for it to be 1 hour, but then IntelliPet team did not agree. Basically, tomorrow I have a family function, and that's why I won't be available for entire time. But then again, in the next weekend we have full sessions. So if anything is pending, I'll take it up. So for today, only half an hour is remaining, and then let me complete this part. Please look at the recordings in your free time, and I hope you'll get it. So tomorrow, what I'll do, maybe one problem. If everyone give it a try, and tomorrow I'll take up one problem so that you get more clarity about LC selection, not a big deal. But then you have to understand that I squeeze some part in motor and motor controller, right? Because something I am expanding, somewhere I have to balance for the time. So this is the PI controller, right? Let me just explain briefly again. PI controller is a subject of control system. Those who have taken a course on control system in electrical engineering, you must know control system is a semester long course, right? So we cannot cover again everything in detail, but let me try to give you some idea what it is done in PI controller. So the system we wanted to control, DC-DC converter, my challenge is input voltage varies from 40 to 54 volt, okay? Output voltage, we want it to be 12 volt. Alright, so what we're going to do, in a PI controller, in the plus symbol, we're going to give 12 volt, okay? That is V0 reference. Actual V0, we're going to measure. So here, we are going to connect a voltage sensor. Or in your terminology, some of you may be familiar with, that's a voltmeter. Okay. So voltmeter will show you the reading. Voltage sensor, what it will do, basically it will be placed in the circuit and it will read that value and it will pass on to the microcontroller directly. Okay. So all this PI controller, how we are going to implement it, it will be inside your microcontroller. Eventually I'll show you in a code level implementation, it will be just some lines of code in modern microcontrollers. Okay. So this V0 star minus actual V0, that is the error. This error will go to two parts. One will be just multiplied by a factor Kp. This is just a constant number. Okay. So what will be the output here? It will be Kp into error. Simple math, right? Output of this P controller will be Kp. Kp is that constant number, right? Into error. Then for the integral part, we are going to use another constant ki. Again, it's a constant. Then there will be an integrator. Now all of you have studied integration in class 12, right? So this will, so integrated output, what it will be? It will be integration of ki into error dt plus I0. Basically, any integration has the previous value. Integration is nothing but previous value plus current integration factors. So this will be added together and this will give the reference value. Generally, before we generate reference value, there will be a limiter block. I'll tell you why. And then this goes to the comparator and then you get the pulse. Okay. So let's go slowly. At the PI controller output, there will be a limiter. As the name suggests, what the limiter will do? It will limit. So PI controller, whatever it is generating, the limiter will limit in a range. Now you can ask the question, why limiter is required? See, your sawtooth signal, it will be varying between 0 to some peak value, right? So for example, let's say it is 100 and minimum value is 0. So do you think if I generate a reference value 1000 or 1 lakh, does it make any sense? Answer is no, right? Because I want my reference signal to be within the sawtooth signal. So I want my reference signal somewhere here, in between these two values, right? Then I can compare. So let's say 0 to carrier peak. So if my reference signal is minus 100, comparator has nothing to do, right? So that's the reason we always put a limiter. The limiter value will be generally, ideally 0 to carrier peak value. Or similar to this. Sometimes you don't apply entire carrier, maybe you want to make it limit within, let's say, 80% of the carrier value. There are some harder reasons, I will come later if time permits. So what I have to say is very logical reason. Sawtooth signal is varying between a range, right? So I want my reference signal to be within that range. There is no point of generating a reference signal which is much higher or much below my carrier range. So that limiting function will be done by the limiter, okay? Now, coming to this first part, there is P controller, there is integral controller, right? They are added together. So this top part you see, this is the P controller. P stands for proportional. Why proportional? Again, math basics. If output is proportional to the input, basically there is a constant multiplier, right? So this is P controller. The bottom part is doing integration. So it is called integral, right? Controller. So in total, it is PI controller. So it is basically proportional plus integral controller. Do note their output are added, right? Not subtracted or multiplied. Both P controller and I controller, they have same input, the error. But the output are added together. That generates the reference signal. I hope this point is clear. So some questions we need to address. How to select KP, PI. Okay? I don't know, right? How to select. I understand that it is a constant number. It may be 1, it may be 1 lakh, it may be 1 crore, it may be 0.0001, something, right? Anything. But how do I decide? So there are multiple ways to decide these KPI values. Okay? Most commonly used techniques are trial and error. As the name suggests, you keep changing it, right? And hopefully it will work. There are some standard methodologies plus standard methods. For that, you have to study control system. So basically what we do, we get the transfer function of the system of the plant. Plant is that buck converter. Then we put it into a border plot. We see the frequency response. Based on that, we see the gain margin, phase margin, all those things. And looking into that, we do the stability analysis. And to make the system stable and I get my desired gain margin, phase margin, these KPI values are selected. Okay, so first, this buck converter, you get a transfer function of this. Output voltage versus duty ratio. Buck converter is a non-linear system. A lot of switchings are happening, right? So first you have to linearize it. So those, again, from non-electrical background, most likely it will be very difficult for you. Okay? Then you have to study a concept called border plot. So each of the topic that I'm talking about, for each of the topic you need to, even if you have electrical basic background, you need 3-4 hours, at least for each of them. If you are from non-electrical, you need months typically. Okay? So that's why people generally don't go to this path, because it takes a lot of time and there are a lot of theoretical understanding and all. So that's why for quick method, people generally go with trial and error. Okay? But then problem with trial and error is that you don't know where to start. Shall I start with 1 or 1 lakh? Right? And there are infinite possibilities. There are 2 variables. You don't know what to do, right? So that's why there are some standard procedures, how to start and how to stop. So for that, I gave you a detailed documentation to help you. step by step I mentioned what is a standard. Of course, it's not by me. These are already existing. I'm just trying to convey through the simulation. And so first, whether shall I tune KP or KI or both of them, where to stop. So all these things you see, I mentioned step by step. Okay. So go through them. In fact, all the simulation file, which one to set, how, all these things I have given so that you understand it. But again, let me tell you, this will take hours time, right? So if you're happy, please invest your time. You'll get all the answers. But don't expect that you'll spend 5-10 minutes and you'll get the answers. Not possible. These are a lot of concepts involved, right? So here you can see, I explain how easily you can set these KPI values without spending too much time. So this step by step, for example, generally we do first P controller, then we do tuning integral part, right? So then where to stop, how to start, those things in detail I have mentioned. Of course, I cannot go line by line now. This will take a huge amount of time. So please go through them and see. I explain everything in a very simple English with all those plots also, so that you get an idea. I gave you the simulation file. I gave you step-by-step guideline. I gave you the result, what to expect. So what you have to do is spend time, follow all this. Hopefully you'll get it. Okay. First decide KP, then decide KI, then do both of them and tune it. Okay. So again, let me explain briefly about this magical controller. Especially, see, a P controller part is very simple. Let me just continue for another 5-10 minutes, then I'll give you my cases also. So P controller is, as you understand, it is a very simple control. So your reference signal, for time being, I'm neglecting that limiter. And this will give you the gain bus. So this is only P controller. Okay. So what P controller will do, see, whatever is your error, it will multiply it by this KP. Okay, and that's how you're going to get the reference signal. So error into KP, that will be a reference signal if you use only P controller. So reference signal will be nothing but KP into error. Now, what do you want from the controller? What the controller should do? Or what are the expectations or objectives? So first objective is to make the error 0. So error 0 means your V0 star will be same as V0, right? Or V0 will be same as V0 star. That is what we mean, the error to be 0. That is our main expectation, right? Error 0 means actual output voltage will be same as desired value, that is 12 volt. That is what we want. Simple, right? Second, we want this to happen fast. Okay, we want it to happen fast. I want it, let it be now. What is the point if I have it after 1 year? No point, right? So we want it to be fast. We want the system to be stable, and so on, for simplicity. Okay, but eventually what we want is we want the error to be 0. Isn't it? That's my whole perspective of this closed loop controller. I want to go at 10 kilometers per hour. I want to go at that speed. Then my error is 0. Now, in this case, just we'll take fixed input. V input is 48 volt, right? V output we want is 12 volt, just for simplicity. So D we want is 12 by 48. That means 0.25. We discussed this earlier also. So what is the value of D we want to achieve this? Is 0.25. But problem is that with P controller, it is not possible. Why? Okay. See, for a P controller, if error equal to 0, what will be the reference signal? Reference signal is error into KP. So it will also become 0. Isn't it very simple? I want error to be 0. But if error goes to 0, the reference signal for P controller, this will also become 0. So it will be something like this. I have my sawtooth carrier and my reference signal is sitting here. So what will be my duty ratio? It will be 0. Right? Anything you multiply with 0, it will be 0, right? Unless KP is an infinite number. For practical hardware implementation, we cannot achieve infinite number, right? So it has to be finite. So if I want error to be 0, P controller output will also go to 0. So then your duty ratio will become 0. So it is not possible. Okay? So that's why we say that P controller can't eliminate steady state error. So basically, steady state is, let's say we created some disturbance in the system, there will be some transient demand. Effectively, it has to be, in steady state means no transient, smooth operation, right? Simple terms. Some disturbance, settle down, smooth performance. That is the steady state. So can we achieve error 0 with P controller? No, because as soon as error goes 0, P controller output will also go to 0, right? So that's how we cannot eliminate steady state error. Can integral controller eliminate steady state error? Yes. That is the beauty of integral controller. I'll show you how. So before that, again, basics of integration. Okay. So for a function ft, its integral is we generally show by this, right? Integration f of t. Simple. So we take it like we did in class 12. Again, I'm not going into integral calculus and all. It will take huge amount of time. I also forgot a lot of things. But just revise how integral calculus started and all these things. Right? It may help you. So remember, always integration, right? It starts with taking integration of something, and then it also comes with the previous value. That is the important part. Always an integration, right? If you want to integrate it, let's say from 0 to t. So what is the previous value? What is the previous value at time t equal to 0? That is the beauty of integration. It has the memory effect. Okay. So then integration, again I'm saying, it has this previous value effect, right? Initial value, and then you do this integration. So let's take in simple terms, without going into much technical detail, let's see. If integrator input is something, what will be integrator output? So what I'm trying to